Hello and welcome to Grace tutorial. In this video lecture, we will be discussing about the fifth part of the chapter Aldehydes, Ketones and Carboxylic acids. And here we are going to discuss the entire things about the properties of, first of all, aldehydes and ketones. Well, basically the properties includes two types of properties. One is the physical property, another is the chemical property. Well, in the physical property, what are we going to study? In the physical property, we are going to study about, the states. We are going to study about the solubility, the boiling points, the melting points. So, all these properties come under the physical properties. That's why, first of all, we will discuss the physical properties of aldehydes and ketones. Well, you see, except formaldehyde, well, the formaldehyde is the first member of the aldehyde, no doubt, right? So except formaldehyde, all other aldehydes and ketones up to C11 are liquids. That means formaldehyde is a gas. So except this formaldehyde, all the other aldehydes and ketones are up to C11. That means up to carbon 11 are liquids, and higher members, the higher members are there, the higher members are solids. That means the higher members of aldehydes and ketones are solids. That means this first, the first statement gives you a clear idea about the state of the aldehydes and ketones. The formaldehyde is a gas. And except that formaldehyde, all other aldehydes and ketones except carbon 11, up to carbon 11, those are liquids and higher members are solids. Well, if you look at the second point of the physical property, the lower members of the aldehydes and ketones are soluble in water. That means if the alkyl chain increases, then the solubility gradually decreases. So the lower members of aldehydes and ketones are soluble in water. That means now the question is, can aldehydes and ketones are soluble in water? Of course. The lower members of aldehydes and ketones are soluble in water, but the higher members, which consist of the more number of the alkyl groups, they cannot get soluble in water. That is about the solubility of aldehydes and ketones. Now, boiling point. We'll talk about the boiling point. They have higher boiling points than alkanes of comparable molecular masses due to the polar nature of the carbonyl compounds. Since the carbonyl compounds are polar in nature, due to the stronger dipole-dipole interactions exists between the two, that's why the boiling points, they have the higher boiling points. So who have the higher boiling points? The aldehydes and ketones have the higher boiling points because due to the polar nature of a carbonyl group. That means the carbonyl compound. Due to the polar nature of this carbonyl compound, a strong dipole-dipole interaction exists in the aldehydes and ketones. That's why they have higher boiling points than alkanes. But if you will compare the boiling points of the aldehydes and ketones with acids as well as the alcohol, the boiling points are said to be low. That means comparing to the acids as well as the alcohols, the boiling points of aldehydes and ketones are low because the dipole-dipole interactions are not so strong in them, as intermolecular hydrogen bonding. That means, you see, aldehydes and ketones have higher boiling points than alkanes because due to its polar nature of carbonyl compounds, the stronger dipole-dipole interaction exists, and as a result, the high energy is required to overcome these interactions. That's why the boiling point rises. But the boiling point decreases. The aldehydes and ketones have the lower boiling point as we comparing to the acids as well as the alcohols because the interaction is not so much strong as intermolecular hydrogen bonding. Well, this is all about the physical properties of aldehydes and ketones. Now we will discuss the chemical properties of aldehydes and ketones. Well, if you look at the chemical properties of the aldehydes and ketones, basically initially I had discussed about the structure of the carbonyl group. That means the aldehydes and ketones contains the carbonyl group, that means CO group. This is the carbonyl group, and here in this carbonyl group, since the oxygen is more electron negative, that means the shared pair of the electrons will be shifted more towards the oxygen atom. As a result, there will be a slight negative charge will be created in the oxygen atom. Similarly, in case of the carbon, since it loses the pair of electrons, there will be a slight positive charge is created in the carbon atom. That means the polarity increases. So where the polarity basically increases, this is a polar compound. So we had to discuss initially that what do you mean by polar compounds and what do you mean by non-polar compounds. The compounds are said to be non-polar if the electrons are equally distributed between the two atoms. On the other hand, the compounds are said to be polar if the electrons are not equally distributed between the two atoms. The two atoms are there. The atom which is having the high electronegativity attracts the electron towards itself. Since the oxygen is high electronegative than that of carbon, so it attracts the pair of electron towards itself. As a result, a partially negative charge is created. Similarly, a partial positive charge is created in the carbon since it loses the electron. That means a polarity increases in the carbonyl compound. And due to this polar nature, the carbonyl, that means the center, the carbonyl has two active centers. One is, the carbon atom of the carbonyl group will be attacked easily by a nucleophile. It will be attacked easily by a nucleophile because the carbon atom is an electrophile, because the carbon atom is partially positively charged. Partially positively charged, that's why it can be easily attacked by the nucleophile. Similarly, here the oxygen atom, it occupies a partially negatively charged particle. That means since it is having the partially negatively charged, it is rich in electron. That's why this will be attacked by an electrophile. So what are these electrophiles and the nucleophiles? These are the different reactive intermediates. Electrophile means electron loving species or electron deficient species. On the other hand, the nucleophile means nucleus loving species or the electron rich species. Since the carbon atom, due to the development of the polarity nature, a partial positive charge is created in the carbon atom. That's why it acts as an electrophile. As a result, the nucleophile attacks the electrophile. The nucleophile can attack the carbon atom of the carbonyl group. And since it is negatively charged particle, it can be easily attacked by the electrophile. In this way, the carbonyl compound has two active centers. One, it can be attacked by the nucleophile, and the oxygen can be attacked by the electrophile. And finally, this product, the product is obtained like this. So when a nucleophile attacks the carbon atom of the carbonyl group, then the nucleophile will be attached in so way, and finally we'll get the product like this in the when the reaction is fast. This is what all about. But now the question is, which one are more reactive? Whether aldehydes are more reactive or the ketones are more reactive. If we talk about the reactivity of aldehydes and ketones, that we need to focus much more about the aldehydes, because the reactivity of aldehydes are more than that of the reactivity of the ketones. And if we take the aldehydes, we have formaldehyde, we have acetaldehyde, or let us take the acetaldehyde, formaldehyde, and this is aldehyde, and this is also this is ketone. If you observe it very carefully, here no alkyl group is there. In case of formaldehyde, no alkyl group is there. But if you observe here one alkyl group is there. But in ketone, here two alkyl groups are there. So you need to remember, this alkyl group is basically an electron releasing group. Electron releasing group, or we can say electron repelling group. So R is electron releasing group or electron repelling group. So what happens here, since if the alkyl group increases, if the alkyl group increases, there may be a chance of increasing the stability of the compound, but the stability is inversely proportional to reactivity. That means if the stability increases, the reactivity decreases. As a result, since the reactivity, if you talk about the formaldehyde and this aldehyde as well as the ketone, which one is more reactive means what do you say that? Yes, the formaldehyde is more reactive because it contains no alkyl group. Since it contains no alkyl group, that is, it has no electron releasing group. As a result, the stability decreases, no doubt, but the reactivity increases. But as we come from here, that the reactivity decreases, the ketone, the reactivity of the ketone is much more lower than that of the reactivity of the aldehyde. Because here in this case of the aldehyde, we have only the one R, that is one alkyl group, that is electron releasing group or electron repelling group. But here in case of this ketone, we have two alkyl groups. As a result, due to the plus I effect, that the reactivity decreases as the alkyl group increases. So if you ask the question, aldehydes and ketones are both the carbonyl compounds. Both are carbonyl compounds, both are organic compounds, but which one is more reactive means what do you say? The compound which is having the least alkyl group, the compound which is having more alkyl group, the stability increases, of course, no doubt, but the reactivity decreases. That means the ketone's reactivity is low than that of the aldehyde's reactivity. That means aldehyde is more reactive than that of the ketone due to the presence of more alkyl groups in case of ketone. So that's all about the reactivity of aldehydes as well as the ketones. So since since it shows the nucleophilic addition reactions. Since the carbon atom of the carbonyl group shows the nucleophilic addition reactions, let us look at some of the nucleophilic additions reactions since it is attacked by the nucleophile. The first one we have the addition of hydrogen cyanide, that is HCN, hydrogen cyanide, or we can say hydrocyanic acid. Well, this is formaldehyde, HCHO. When the hydrogen cyanide attacks the formaldehyde, when the hydrogen cyanide reacts with formaldehyde, what happens? Here the formaldehyde cyanohydrin, yes, formaldehyde cyanohydrin is obtained. Here, if you will dissociate these two, you will get H plus and Cn minus, right? And since this oxygen is partially negatively charged one. If you look at here, the oxygen is partially negatively charged one. That's why it will be attacked by an electrophile. So this is basically an electrophile. H plus is an electrophile, and this oxygen will be attacked by the electrophile. As a result, we get OH. Since OH, and finally we have cyanide. This cyanide, as a result, the pi bond of this one will be broken and it forms a sigma bond. That means when the HCN reacts the formaldehyde, then the pi bond between the carbon and oxygen which is present will be broken and a sigma bond is formed, and Cn is connected to that. And how the OH is formed here? Because this HCN, this H plus is basically an electrophile, and this is more electronegative. Oxygen atom is more electronegative. That's why it can be easily attacked by the electrophile, and finally it gives formaldehyde cyanohydrin. Similarly, if you will take CH3H, this is acetaldehyde. If you will take acetaldehyde, if the acetaldehyde is attacked, similarly we'll get the OH will be attacked here. That means CH3H, now OH, and here it is Cn. And since we have taken acetaldehyde, when the hydrogen cyanide reacts with acetaldehyde, it gives acetaldehyde cyanohydrin. Similarly, if you will take if you will take acetone, CH3 C double bond O plus HCN. If you will take this acetone, the same exactly it happens. Here OH and Cn. So this is acetone and hydrogen cyanide, and the product is acetone cyanohydrin. In this way, the addition of the HCN takes place. Of course, this is a nucleophilic addition reaction, but this is the first addition, that is the addition of HCN, that is hydrocyanic acid. So that's all about the first one of the nucleophilic addition reactions. And now we will discuss another example of the nucleophilic addition reactions. If we look at the addition of sodium bisulfite, suppose you see we have formaldehyde. So what is the formula for formaldehyde? HCHO. If you will add this sodium bisulfite, NaHSO3, you see this H, the hydrogen, it will be attacked by the oxygen, and as a result the pi bond of this one will be broken and a sigma bond is formed. That means it gives OH, then NaSO3. So this is formaldehyde. Sodium bisulfite. Finally the product arises formaldehyde sodium bisulfite. Formaldehyde sodium bisulfite. This is the first one. And suppose if we will take acetaldehyde, and react with NaHSO3, then what do we get? Exactly the same thing happens here, but only the CH3 will be added, OH and NaSO3. So what's the name of this compound? Acetaldehyde sodium bisulfite. Similarly, if I take acetone and reacts with NaHSO3 sodium bisulfite, you remember NaHSO3 this is HSO3 means bisulfite. HSO3 means bisulfite. FPHITE. But SO3 means actually sulfite. So H is there means hydrogen sulfite, or we can say bisulfite. If SO4 is there, then we can say sulfate. If SO2 is there, then sulfur dioxide. If SO3 is there, we also can say sulfur trioxide, and there is sulfur, in this way we can use the various things. So this is NaHSO3 sodium hydrogen sulfite, or we can say sodium bisulfite. So what happens here? CH3, COH, and finally it gives NaSO3. So acetone sodium bisulfite. Acetone sodium bisulfite. And this is acetone. And here it is acetaldehyde. So when the acetaldehyde reacts with sodium bisulfite, acetaldehyde sodium bisulfite is obtained. Similarly, when acetone reacts with sodium bisulfite, acetone sodium bisulfite is obtained. So this is the another example of the addition of the sodium bisulfite, that is NaHSO3. Well, now we look at the another one, that is addition reactions followed by the elimination of water. So before we discuss about the addition nucleophilic addition reaction followed by the elimination of water, first of all let us look at the addition of Grinards reagent, that is RMGX. Well, first example that we have taken, that is formaldehyde. When this formaldehyde reacts with methyl magnesium bromide, then this methyl, since it is an electrophile, it will be attacked by the oxygen atom. Sorry, it will be attacked by the carbon atom. Yeah, and here the pi bond will be broken and a sigma bond is formed. That means the CH3 will be attached here, and this O is there, and this is MgBr, magnesium bromide. OMgBr is obtained. This is basically an addition product. And on further hydrolysis, it gives the primary alcohol, that is ethanol. Ethanol, which is the primary alcohol, and magnesium hydroxybromide is obtained. Similarly, if you will take acetaldehyde, then react with CH3MgBr. What do we get? First of all, you will get the addition product. OMgBr. And if you will hydrolyze that one again, on hydrolysis, further hydrolysis, that it gives the secondary alcohol, MgOH-Br, magnesium hydroxybromide. The secondary alcohol, that is propanol. Secondary alcohol is obtained. This is acetaldehyde. Similarly, if you will take acetone, what happens? CH3, say double bond O, and CH3MgBr. You will get the addition product. OMgBr. And on hydrolysis, you will get tertiary butyl alcohol, that is butanol, that is tertiary alcohol, plus MgOH-Br, methyl magnesium bromide. So this is what the product, and these are the addition product. Addition products. This is acetone. This is about the addition of Grinards reagent. Well, now we'll look at the nucleophilic addition followed by the elimination of the water. So if we look at the nucleophilic addition followed by the elimination of water, the first one we have reaction with hydrazine. Hydrazine. So what is the formula for hydrazine? NH2, NH2. So the formaldehyde is there. If the formaldehyde is reacted with hydrazine, then the water is eliminated. The water is removed from here, and you get this is called formaldehyde hydrazone. Hydrazone with the elimination of water molecule. Similarly, if you will take acetaldehyde and reacts with hydrazine, then you will get the water molecule will be eliminated from here, and CH3HC double bond and then H2, that is acetaldehyde hydrazone. Acetaldehyde hydrazone. Similarly, if you will react with acetone, water is removed from here, and it gives CH3 C double bond NnH2. Finally, water is removed from here. This is acetone hydrazone. So the question is, when the hydrogen reacts with formaldehyde, what it obtains? It gives formaldehyde hydrazone. When the acetaldehyde reacts with hydrogen, it gives acetaldehyde hydrogen. When the acetone reacts with hydrogen, it gives acetone hydrogen. So all these are the hydrogen products are obtained. But what is the thing important we need to remember? This is the nucleophilic addition reaction, which is followed by the elimination of the water molecule. That is with the reaction with hydrogen. Now we will look at the reaction with phenyl hydrogen. So if we look at the reaction with phenyl hydrogen, this is the formula for phenyl hydrogen. It's very simple. Hydrogen means NH2 NH2, and one hydrogen will be replaced from here and the phenyl group is attached. So that is C6H5NH NH2. This is phenyl hydrogen. So the formaldehyde is there with me. When this formaldehyde reacts with phenyl hydrogen, that means H2N NH C6H5. Why did I write so? Because I can it will be easy for me to eliminate the water molecule. Presence of little bit acid, you will get NNHC6H5. Then with the elimination of the water molecule. This is phenyl formaldehyde phenyl hydrogen. Formaldehyde phenyl hydrogen. Similarly, if you will take acetaldehyde CH3CHO, reacts with the same phenyl hydrogen H2N NH C6H5, then the water will be removed. NNHC6H5 plus water. This is acetaldehyde phenyl hydrogen. Phenyl hydrogen. Since acetaldehyde has been taken and reacted with phenyl hydrogen, that's why the name is acetaldehyde phenyl hydrogen. Well, if you will take acetone, what happens you already can guess, and react with H2N NH C6H5. If you will react H plus, then it gives acetone this is acetone phenyl hydrogen. Acetone phenyl hydrogen, and this is acetone. So reaction with phenyl hydrogen is also easy. That formaldehyde reacts with phenyl hydrogen, with the elimination of the water molecule remaining you will put the same, that is formaldehyde phenyl hydrogen. If acetaldehyde reacts with phenyl hydrogen, it gives acetaldehyde phenyl hydrogen. Similarly, if acetone reacts with phenyl hydrogen, it gives acetone phenyl hydrogen. So these are the three different examples with the reaction with phenyl hydrogen. Now we'll look at the another reaction, that is the reaction with hydroxylamine. If we will look at the reaction with hydroxylamine, what is the formula for hydroxylamine? NH2OH. Well, suppose I have formaldehyde, HCHO. This formaldehyde reacts with hydroxylamine, H2NOH. Water is eliminated from here. As a result, NOH. It's nothing but the H2 of this hydroxylamine reacts with oxygen atom and it finally forms water, and the water is removed from here and HHC double bond NOH. This is formaldehyde oxime. Formaldehyde oxime. Similarly, if you will take acetaldehyde, then what the product is obtained? See, NOH plus water. So since you have taken acetaldehyde, this is called acetaldehyde oxime. If you will take acetone, water is removed from here, and finally it gives elimination of water. This is acetone oxime. So the product named with oxime is obtained here. When formaldehyde reacts with hydroxylamine, formaldehyde oxime, it's nothing but water is removed, that's it, and remaining as it is same. So when acetaldehyde reacts with hydroxylamine, acetaldehyde oxime is formed. Similarly, when acetone reacts with hydroxylamine, acetone oxime is formed, followed by the elimination of the water molecule. So this is all about the reaction with hydroxylamine, that is NH2OH. And next we will look at the reaction with Brady's reagent.